Right now, somewhere above you, or perhaps behind a curtain, behind a wall, behind the soft dark of closed eyes, light is arriving. It has been traveling for a little over 8 minutes, in a straight and patient line, through the cold nothing of space, and now it is settling onto the world around you, whether you can see it or not. Some of that light warmed the pavement outside today. Some of it slipped through a window and touched the back of a chair. Some of it, filtered and dimmed and softened by the time it reaches you now, is simply part of the air, part of the quiet hum of a planet that has been receiving this light every single day for longer than there have been days to count. You don't have to notice it. You don't have to do anything about it at all. It arrives whether you're paying attention or not, the way your breath keeps coming, slow and easy, whether you think about it or not. Let it arrive. Let your shoulders soften into whatever is holding you right now, the mattress, the pillow, the arm of the chair, and let's use that quiet arriving light as our starting point tonight, because it happens to be one of the oldest, steadiest facts in your life. That light has a source, and the source is the reason there is a today at all, the reason there is warmth and shadow and morning. Tonight, we're going to talk about that source and about the family of worlds that travels along with it through space, forever. We're going to talk about the solar system. Not quickly and not all at once. Slowly, the way you'd walk through a house you've lived in for years but never really looked at closely. Room by room, in no hurry, noticing things you'd somehow never noticed before. There is no test at the end of this. There is nothing to remember, nothing to hold on to. If your mind drifts off before we're finished, that's not a failure of the explanation. That's the whole point. So let's start simple, the way the earliest people who looked up at the sky had to start. Imagine you knew nothing about any of this. No telescopes, no satellites, no photographs taken from a spacecraft slipping past a distant moon. All you had was your own eyes and the sky, night after night, for your whole life, and the lives of your parents and their parents before them. What would you actually see? You would see a bright light that rises and sets in a very reliable rhythm, warm during the day, absent at night. You would see, once the sky went dark, thousands of tiny points of light, scattered and still, holding their positions relative to one another with such patience that you could use them to navigate a ship across an ocean, or to know when to plant your crops. The ancient Egyptians tracked one particular star, low on the horizon just before dawn, to know when the Nile was about to flood and enrich their fields. The stars, in other words, behaved like a fixed backdrop, trustworthy, unmoving, relative to each other. But if you watched closely, for months, for years, you would notice something odd. A handful of those points of light didn't behave like the others. They wandered. They drifted slowly against that fixed backdrop of stars, sometimes speeding up, sometimes slowing down, and every so often doing something that must have seemed almost impossible, moving backward for a while before resuming their normal path. The ancient Greeks noticed this too, and they had a word for these wandering lights. They called them planetes, which simply meant wanderers. That word is still with us. It became our word planet. So even the name we use tonight is really just an old, honest description of something people watched with their own eyes, long before anyone understood what was actually happening. What was actually happening, we now know, is both simpler and stranger than anyone guessed for a very long time. Those wandering lights were not lights in the sky at all, not the way the stars are. They were worlds, places, some of them rocky, some of them made almost entirely of swirling gas, some of them cold enough that their surfaces have never once felt warmth. And they weren't circling around us, around the Earth, the way it looked from where those early observers were standing. They and we were all circling around something else, something enormous and blazing, sitting at the center, holding everything in a slow, patient, endless orbit around itself. That something is the sun, and it is worth pausing here, gently, because the sun is so familiar, so constant, so woven into ordinary life that it's easy to stop actually seeing it. But the sun is a star, an ordinary star, as stars go, one of hundreds of billions in our galaxy alone, remarkable mostly for the fact that it happens to be ours. It is a sphere of hydrogen and helium, so massive that if you could hollow out the Earth and start dropping identical Earths inside it, one after another, you would need more than 1,000,000 of them to fill the space. Every bit of warmth you have ever felt on your skin from sunlight, every log fire, every gallon of gasoline, in a very real sense every meal you have ever eaten, traces its energy back to that one star, quietly burning at the center of everything. Around the sun, held there by nothing you can touch or see, held there simply by the pull of its own enormous mass, the planets travel. Mercury, closest in, scorched and cratered. Venus, wrapped in thick, choking cloud. Earth, our blue and green exception. Mars, rust-colored and quiet. Then, after a wide gap of scattered rock and rubble, the giants begin. Jupiter, vast enough to swallow every other planet combined, and still have room left over. Saturn, wearing its wide, glittering rings like a hat it never takes off. Then Uranus and Neptune, pale and distant, so far from the sun's warmth that they were unknown to any human being until telescopes powerful enough to find them were finally built. And all of this, every planet, every moon circling those planets, every scrap of ice and dust drifting in the outer dark, all of it moves together. That's the detail I want you to sit with tonight, more than any list of names or distances. This is not a scattered collection of separate objects that happen to share the same neighborhood. It behaves like a family, in the oldest sense of that word. Everything in it is connected by the same quiet pull, the same shared history, the same slow orbit around the same star. The Earth is not out here alone. It never has been. It is one member of a much larger, much quieter household, all moving together through space at almost unimaginable speed. And yet, from where you're lying right now, everything feels completely, perfectly still. That stillness is real in its own way. You are not being flung around. You are not gripping the arms of your chair to keep from falling. And that peaceful feeling, that sense of being anchored and steady while an entire system of worlds turns slowly around a distant fire, is not an illusion you need to correct. It's simply a different scale of truth living alongside the one you can feel. Both are true at once. You are still, and you are moving. You are alone in a quiet room, and you are part of a family of worlds that has been traveling together for more than 4.5 billion years. We'll walk through that family slowly, one part at a time, over the rest of tonight, not to memorize it, just to understand it a little better, the way you might slowly get to know the layout of a house that's been yours all along. But first, let's go back to where we started. That soft, silent light that reached you a few minutes ago, the light that's been arriving all night, is only the very beginning of the story, because before there could be a sun to send that light out at all, there had to be a much earlier moment, a moment of dust, a moment of slow, quiet gathering, out in the cold and the dark, long before there was anything here to feel warm at all. Let's go there now, gently, because it's a good place for your mind to rest. Picture, if you can, a very large, very cold cloud, floating in the space between stars. Not a cloud like the ones that drift over your house on an ordinary afternoon, This one was made of gas and dust, spread out over a distance so wide that light itself, moving as fast as anything can move, would have taken many years just to cross from one side of it to the other, and it was cold, colder than anywhere on Earth ever gets, colder than the deepest part of any winter you've ever felt, down near what scientists call absolute zero, the point where atoms themselves barely have the energy left to move at all. This cloud had probably been sitting there, quietly, for a very long time, doing more or less nothing. Clouds like this are common, in the vast, slow sense that anything in space is common. They drift, they cool, they wait, though of course a cloud doesn't wait in any way that involves patience, or intention, or knowing that anything is coming. It simply exists, spread thin across the dark, until something disturbs it. And something did. Perhaps a nearby star reached the end of its life and exploded, sending a wave of pressure rippling outward through space, the way a sound moves through still air, except this wave carried enormous force with it. Or perhaps the cloud simply drifted through a denser region of the galaxy and felt a gentle squeeze from every direction at once. We don't know the exact trigger for our own cloud, the one that would eventually become the sun and the earth, and everything else we've been talking about tonight. But something nudged it, something tipped the balance, just slightly, from stillness toward motion. And once that happened, gravity took over. Gravity is a patient force. It doesn't need to be strong to eventually win, given enough time and enough material to work with. Every bit of gas and dust in that cloud was pulling gently on every other bit, the way you're being pulled, ever so slightly, toward the walls of the room you're lying in right now, and toward every object in it, even though you can't feel it happening. Most of the time, in most places, that pull is far too weak to matter. But in a cloud that size, with that much material, spread across that much space, the pull adds up. And once part of the cloud started falling in on itself, even slightly, that part became a little denser, and denser material pulls harder, so it drew in more material, which made it denser still, which let it pull even harder than before. It was a slow kind of snowball, rolling not through snow, but through cold gas and scattered dust, growing, because growing made it better at growing. This process took an extraordinarily long time by the standards of a single evening, though it happened quickly by the standards of the universe. Over what was likely several 100,000 years, the cloud began to collapse toward its own center. And here's something worth sitting with for a moment, because it's a little counterintuitive. As all that material fell inward, it didn't fall in straight lines, like rain falling toward the ground. It was already turning, ever so slightly, the way almost everything in space seems to be turning, ever so slightly, in some direction or another. And when something that is spinning very slowly gets pulled in tighter and tighter toward its center, it has to spin faster. You may have felt a version of this yourself if you've ever watched a figure skater pull their arms in close to their body during a spin and seen them suddenly whirl faster than they were a moment before. Nothing new was added to make them spin faster. The same skater, the same body, simply gathered in, and the spin quickened on its own. The collapsing cloud did something similar, only on a scale that dwarfs any ice rink, any skater, any single human motion you could compare it to. So as the cloud pulled in tighter, it began spinning faster, and here is where the story becomes a disc instead of a ball. Material falling straight in toward the center, along the axis the cloud was spinning around, had a clear, uncrowded path. But material trying to fall in from the sides, from what you might think of as the equator of that spinning cloud, ran into a problem. It was moving too fast, sideways, to fall straight in. The same spin that was speeding up was also pushing outward. in a sense, against the material trying to collapse inward from those directions. The result was a flattening. Over time, that great spinning cloud settled from something roughly round, like a loosely packed snowball, into something much flatter, like a slowly turning plate, or perhaps like the shape you get if you spin a ball of soft dough on your fingertip and watch it flatten and spread as it turns. This flattened, spinning shape is what scientists call the solar nebula, and it's worth remembering that word gently, without any pressure to hold on to it, because we may come back to it later tonight. For now, just picture it. A wide, thin, turning disk of gas and dust, glowing faintly with the heat of its own collapse, with almost all of its material gathered into a dense, hot clump at the very center. That clump at the center is where our story of the sun really begins. As more and more material fell inward, toward that central clump, it grew denser and denser, and as gas grows denser, it grows hotter, the way the air inside a bicycle pump warms slightly when you compress it quickly with your hand. Except, this was compression on a scale beyond anything you could produce with your hands, or with any machine ever built by anyone, anywhere. And eventually, after enough material had gathered, and enough pressure and heat had built up at the center of that clump, something remarkable happened deep inside it. The hydrogen atoms packed into that center were pressed together so tightly, and heated so intensely, that they began to fuse together, joining to form helium, and releasing, in that joining, an enormous and steady outpouring of energy. That moment, the moment fusion ignites at the heart of a collapsing cloud, is the moment a star is truly born. Before it, you have a very hot, very dense clump of gas. After it, you have a sun. Our sun likely reached that moment a little over 4.5 billion years ago, and once it did, it began doing something it has been doing every second since, without pause, without rest, quietly turning a small portion of its own mass into light and heat, and sending it outward in every direction, including, eventually, toward a small, rocky world that hadn't been built yet. Because remember, the sun wasn't the only thing forming in that disk. All around it, spread out through the flattened, spinning cloud of leftover gas and dust, the same basic process that built the sun was happening in smaller, quieter, more scattered ways. Tiny grains of dust, no larger than the specks of dust you might see drifting in a beam of sunlight through a window, were bumping into each other, gently, again and again, over and over, for reasons that were mostly just simple physics and simple chance. Sometimes they bounced apart, but sometimes, especially if they were moving slowly relative to each other, they stuck, and once two grains stuck together, they were slightly larger, and slightly more likely to catch the next grain that drifted near them, and stick to that one too. It's a strange thing to imagine, if you let yourself really picture it. Somewhere in that early disk, in the cold dark surrounding our newborn sun, the very beginnings of the earth were nothing more than specks of dust, gently colliding, gently sticking, one tiny grain at a time. Let's leave those tiny grains drifting for now, sticking and unsticking in the dark, and turn our attention back to the object at the center of all that activity, because it deserves a slower, closer look. The sun is so familiar to us, so woven into the rhythm of every single day we've ever lived, that it's easy to stop really seeing it. You feel its warmth on your skin. You squint against it on a bright afternoon. You watch it sink below the horizon and call that sunset, without ever quite pausing to consider what an extraordinary thing is happening 93 million miles away to make any of that possible. So let's pause, now, in the quiet, and consider it properly. At its very center, the sun has a core, And this is where that fusion we just described is still happening, right now, as steadily as it has for 4.5 billion years. The core is almost unimaginably hot, somewhere around 15 million degrees, and under almost unimaginable pressure, squeezed by the weight of the entire rest of the sun, pressing down and inward from every side. It's that pressure, more than anything else, that makes fusion possible. Hydrogen nuclei don't want to fuse. They're both positively charged, and like charges repel each other. The same way two magnets pushed the wrong way will push back against your hand. Under ordinary conditions, hydrogen nuclei would simply bounce off one another and go their separate ways. But in the sun's core, the pressure is so extreme and the temperature so high that the nuclei are forced together anyway, close enough that a different force, one that only matters at extremely short distances, takes over and binds them together. 4 hydrogen nuclei, fused in a series of steps, become one helium nucleus, and the resulting helium nucleus weighs very slightly less than the 4 hydrogen nuclei that made it. That small missing bit of mass doesn't vanish. It becomes energy, an enormous amount of energy, in keeping with the relationship Einstein would describe long after the sun had already been doing this for billions of years, that a very small amount of mass, converted, is equivalent to a very large amount of energy. Every second, the sun converts about 4 million tons of its own mass into energy this way. That's a strange number to sit with. 4 million tons, gone, every second, and it has been happening every second for 4.5 billion years, and the sun has lost, by now, only a tiny fraction of its total mass to this process. That tells you something about just how much mass a star like the sun actually has to begin with. That energy, produced in the core, doesn't just leap out into space right away. It has a long journey ahead of it first. Surrounding the core is a region called the radiative zone, and here the energy moves outward the slow way, as light, bouncing from particle to particle, absorbed and released, again and again, in nearly every direction, so that even though it's moving at the speed of light between each tiny step, the overall progress outward is almost absurdly slow. It can take a single packet of light, formed in the sun's core, somewhere between tens of thousands and 100,000 years or more, to finally random walk its way out through the radiative zone. Think about that for a moment as you lie there. Some of the light you might see if you looked at the sun today began its journey before humans had painted on cave walls, before anyone had learned to plant a seed on purpose and wait for it to grow. Once that energy finally reaches the outer portion of the sun, it enters a zone where the gas itself starts to move, physically, the way water moves when you heat a pot on the stove. Hot material rises toward the surface, cools slightly, and sinks back down, in slow, churning cells, over and over, carrying the last stretch of that energy's long journey outward. This is called the convective zone, and it's this rising and sinking motion that gives the sun's visible surface its slightly mottled, grainy texture, if you were ever able to look at it up close and safely, which of course you should never try to do directly with your own eyes. That visible surface, the part we actually see and call the sun, has a name too. It's called the photosphere, and it's not really a solid surface at all. Not the way the ground beneath your feet is solid. It's simply the layer where the gas becomes thin enough, finally, for light to escape freely into space, instead of being absorbed and re-emitted again by the next layer of gas. Beyond the photosphere, temperatures actually dip for a while into a thin layer called the chromosphere, before doing something scientists still don't fully understand, and rising again, dramatically, into the outermost layer, the corona, where temperatures soar to over 1 million degrees, far hotter than the visible surface below it. Why the corona is so much hotter than the surface it surrounds remains one of the genuine open questions in solar science, a puzzle still being worked on, and it's worth remembering, in a narration like this one, that not everything about even our closest star is fully settled and understood. Some mysteries are simply still waiting. The sun isn't a calm, static ball of gas either. It has weather, of a kind, driven by a powerful and tangled magnetic field, one created by the movement of electrically charged material deep within it. That magnetic field twists and knots itself as the sun rotates, and because the sun is made of gas rather than solid rock, different parts of it actually rotate at different speeds, the equator spinning faster than the regions near its poles, which stretches and tangles the magnetic field even further over time. Sometimes that tangled field breaks through the surface, creating darker, slightly cooler patches called sunspots, and sometimes it releases its built-up tension all at once, in sudden bursts of energy called solar flares, or in enormous eruptions of material called coronal mass ejections, which send billions of tons of charged particles streaming out into space. When those particles happen to travel toward Earth and interact with our planet's own magnetic field, they can produce the shimmering curtains of light we call auroras, the northern and southern lights, a genuinely beautiful side effect of a much larger and more turbulent process happening on a star 93 million miles away. And all of this activity, the fusion, the layers, the light, the magnetism, happens around and because of one simple, quiet fact that ties everything else together, which is that the sun is enormous. It contains, all by itself, more than 99% of all the mass in the entire solar system. Everything else, every planet, every moon, every asteroid and comet and stray bit of ice or rock, adds up to less than 1% of the total. And mass, as you'll remember, is what creates gravity. So the sun's gravity, simply by virtue of how much of it there is, utterly dominates the space around it, reaching out for billions of miles, gently but insistently pulling on everything nearby and organizing all of that everything into the great, orderly system we live inside. It's the sun's gravity that keeps the planets in their paths, tracing the same graceful loops around it year after year after year, never flying off into the darkness, never spiraling into the fire. In a very real sense, the sun isn't just the source of the light and warmth that reaches us. It's the reason there's an us for it to reach at all, the quiet, steady anchor around which everything else, including that small, rocky, dust-built world we live on, was allowed to settle into place. Now that we've spent some time with the sun itself, let's drift a little closer to home and take a slow, unhurried tour past the 4 small, rocky worlds that circle nearest to it. These are the terrestrial planets, a name that simply means Earth-like, built mostly of rock and metal rather than gas, and they are, in order of their distance from the sun, Mercury, Venus, Earth, and Mars. 4 siblings formed from the same swirling disk of dust at roughly the same time, out of roughly the same ingredients, and yet, if you were to visit each one, you would find 4 almost unrecognizably different places. It's a little like 4 children raised in the same house who grew up to lead entirely separate lives, shaped by small differences in circumstance that, over billions of years, became enormous differences in outcome. So let's start where the sun's light is strongest and work our way outward. Mercury is the closest planet to the sun, and also, somewhat surprisingly, one of the smallest, barely larger than our own moon. You might expect the planet nearest the sun to be the hottest world in the solar system, and during the day, it certainly is, with surface temperatures climbing past 800 degrees Fahrenheit, hot enough to melt lead. But Mercury has almost no atmosphere to speak of, just the faintest trace of gases, far too thin to trap any heat or move it around the planet. And without an atmosphere acting like a blanket, there's nothing to hold the day's warmth through the night. So when the sun sets on Mercury, the temperature doesn't just drop, it collapses, plunging to nearly 300 degrees below zero before dawn returns. The same planet, the same rock, swinging between blistering heat and bitter cold within the space of a single slow day. And Mercury's days are slow indeed, each one lasting about 176 Earth days from sunrise to sunrise, a strange consequence of the way its rotation and its orbit are gently locked together. Look at Mercury's surface, if you could stand on it safely, and you would see something that looks remarkably like our own moon, gray and heavily cratered, pockmarked by billions of years of impacts, with no wind, no rain, and no shifting ground to ever smooth them away. It's a world frozen in time, a fossil record of the early solar system's violence, preserved because nothing on Mercury has ever come along to erase it. Venus, the next planet out, is often called Earth's twin, and in terms of raw size and mass, that's a fair description, since the two planets are remarkably close in both. But the resemblance ends almost immediately after that. Venus is wrapped in an atmosphere roughly 90 times thicker than our own, composed overwhelmingly of carbon dioxide, and topped with thick clouds of sulfuric acid drifting high above the surface. That thick blanket of atmosphere traps heat with extraordinary efficiency, an extreme version of the greenhouse effect, and as a result, Venus is the hottest planet in the entire solar system, hotter even than Mercury, despite being nearly twice as far from the Sun. Its surface sits at a blistering 900 degrees Fahrenheit, hot enough to melt lead outright, and this heat doesn't really vary between day and night, or between one part of the planet and another, because that dense atmosphere holds and spreads the warmth so thoroughly. The pressure at Venus's surface is also crushing, more than 90 times what we feel here on Earth, equivalent to the pressure you'd experience nearly a mile deep in Earth's oceans. Any spacecraft brave enough to land there survives only a few hours before the heat and pressure overwhelm it. And Venus keeps one more oddity in its back pocket. It rotates backward compared to most other planets, and so slowly that a single day on Venus, one full rotation, actually takes longer than a full year, longer than the time it takes Venus to orbit the Sun. Nobody is entirely certain why Venus ended up spinning the way it does, though some scientists suspect an ancient, colossal collision may have tipped it over sometime in its distant past. It remains one of the solar system's genuine open questions. Then comes Earth, our own planet, and rather than dwell on details you likely already carry with you, it's worth simply pausing on how strange and fortunate its particular balance really is. Earth sits at a distance from the Sun, where water can exist, comfortably and stably, in all three of its forms, as solid ice, as liquid ocean, and as vapor drifting through the sky. Its atmosphere is thick enough to moderate temperature and shield the surface from harmful radiation, yet thin enough to remain relatively gentle, nothing like the crushing weight pressing down on Venus. It's composed mostly of nitrogen and oxygen, an unusual mixture in itself, since oxygen in particular tends to react and disappear over time unless something keeps replenishing it, and on Earth, that something is life itself, plants and countless microorganisms quietly producing oxygen as their surface chemistry hums along in the background. Earth also has plate tectonics, a slow churning and recycling of its outer rocky shell, which most of its neighbors lack, and this constant slow motion helps regulate the planet's climate and geology over vast stretches of time, folding old rock back down into the depths and pushing new rock up to replace it. And Earth has its moon, unusually large relative to its planet compared to most other moon-planet pairings in the solar system, which helps stabilize the tilt of Earth's axis, keeping our seasons relatively steady and predictable across the ages, rather than swinging wildly the way some planets' tilts are believed to do. None of these individual features is entirely unique elsewhere in the universe, as far as we can tell, but the particular combination of all of them together, here, on this one modest rocky world, has so far proven to be quite rare indeed. And then, finally, there is Mars, the outermost of the 4 rocky planets, small, cold, and reddish, colored by iron oxide, essentially rust, scattered across its dusty surface. Mars today is a thin-aired, frigid world, its atmosphere only about 1% as thick as Earth's, made mostly of carbon dioxide, far too sparse to hold much warmth or support liquid water on the surface for any length of time. Average temperatures hover around 80 degrees below zero, though on a summer day near its equator, Mars can occasionally warm to something almost comfortable, briefly touching 70 degrees Fahrenheit, before plunging back into deep cold once the sun goes down. But Mars carries an intriguing history written into its rocks and its landscape, in the dry channels that wind across its surface, looking remarkably like ancient riverbeds, in mineral deposits that typically only form in the presence of standing water, in layered sediments that suggest lakes, even a possible ancient ocean, may once have covered part of its northern hemisphere. Billions of years ago, it seems, Mars may have been a considerably warmer, wetter place, with a thicker atmosphere and flowing water across its surface, not entirely unlike early Earth. What changed remains an active area of study, but the leading idea involves Mars's relatively small size and weaker internal heat, which allowed its protective magnetic field to fade away far earlier than Earth's did, leaving the planet's atmosphere exposed and vulnerable to being slowly stripped away by the constant push of the solar wind, the same stream of particles flowing outward from the sun that we spoke of a moment ago. Without a thick atmosphere to hold on to its heat and its water, Mars gradually cooled and dried into the rusty, quiet desert world we observe today, its rovers rolling slowly across ground that may once have felt a river's current. 4 planets, then, all born from the same disk of swirling material, all built from broadly similar rock and metal, and yet each one carried down its own particular path, by its size, its distance from the sun, its atmosphere, and the small quirks of its earliest history, into wildly different destinies. It's worth sitting with that thought for a moment, the idea that such small differences in starting conditions could lead over billions of years to a scorched world of acid clouds, a frozen and cratered relic, a rusted desert of dry riverbeds, and, somehow, in the middle of it all, a blue and green world quiet enough and balanced enough to hold oceans, forests, and someone drifting off to sleep listening to the story of how it all came to be. From here, our slow journey through the solar system carries us onward, past Mars, across a wide and rubble-strewn gap, toward the beginning of an entirely different kind of world. Past Mars, the orderly spacing of the planets seems to pause for a moment, as if the solar system took a long, uncertain breath before continuing. Between the red planet and the giant world of Jupiter lies a broad, donut-shaped region of space called the asteroid belt, and if you imagine it as a crowded ring of rock, tumbling shoulder to shoulder like stones in a rushing stream, you'd be picturing it far too busy. In truth, the asteroid belt is mostly empty. Spacecraft have crossed it many times, and none of them have needed to dodge so much as a pebble, because even though the belt contains hundreds of thousands of known asteroids, and probably millions more too small or too dark to have been counted yet, they are spread across so much space that the average distance between any 2 of them is something like 1,000,000 kilometers. If you stood on one asteroid, its neighbors would likely be too far away and too small to see at all with the naked eye, just faint points lost among the ordinary stars. It's a lonelier place than the name suggests, a quiet field of scattered stones, drifting slowly around the sun, each on its own long and patient orbit. The word asteroid comes from Greek roots meaning star-like, a name given by the astronomer William Herschel not long after the first one was discovered, because through the telescopes of the early 1800s, these objects appeared only as tiny points of light, indistinguishable at a glance from distant stars, and quite unlike the visible disks of planets. The very first asteroid found, a world called Ceres, was spotted on the first night of the year 1801 by an Italian astronomer and Catholic priest named Giuseppe Piazzi, who was working from an observatory in Palermo, Sicily, and who had actually been compiling a routine catalog of stars when he noticed a faint object that seemed to shift position from one night to the next against the background sky. Piazzi tracked it carefully for a little over a month before illness and bad weather interrupted his observations, and he wrote to colleagues describing what he had found, cautiously calling it a comet at first, though he privately suspected it might be something else entirely, perhaps even the missing planet that astronomers of the time had been hunting for, based on a numerical pattern in the planetary distances that seemed to predict a world should exist in that very gap. For a while, after Piazzi lost track of it, Ceres was feared lost for good, a single faint clue swallowed back into the vastness of the sky. It was recovered only through a remarkable feat of mathematics by a young Carl Friedrich Gauss, who worked out a new method for calculating an orbit from just a few scattered observations, allowing astronomers to predict where Ceres would reappear, and there, when they looked, it was. Ceres turned out to be neither a planet nor an ordinary star, but something new, and it wasn't traveling alone. Within just a few years, astronomers found several more small worlds occupying that same general region between Mars and Jupiter, and it slowly became clear that this wasn't a single missing planet at all, but a whole population of smaller bodies, later given the name asteroids, and later still, once so many had been catalogued, grouped together as the asteroid belt. Ceres remains the largest object there by a comfortable margin, so large and so nearly round, in fact, that it's now classified as a dwarf planet, its own gravity strong enough to have pulled it into a roughly spherical shape over its long history. Most of its neighbors are far less tidy, though, ranging from modest, roughly rounded worlds a few hundred kilometers across, down through countless irregular chunks the size of mountains, city blocks, or, at the smallest end, gravel and dust. If Ceres is like a small, quiet moon set adrift on its own, most of its neighbors are more like broken pieces of something that was never allowed to finish forming, and that idea of something unfinished gets close to what the asteroid belt really represents. For a long time, it was tempting to imagine that the asteroids were the shattered remains of a planet that once existed there and was somehow destroyed, perhaps by a collision or some ancient catastrophe. It's an appealing story, almost the kind of thing you might tell yourself half asleep, a whole vanished world reduced to rubble. But it isn't what the evidence actually shows. For one thing, if you added up the mass of every known asteroid in the belt, all of them together would come to less than the mass of Earth's own moon, and probably only around 3 or 4% of it, which is far too little material to have ever made up a full planet in the first place. The more accurate picture, gently reconstructed from decades of study, is that the asteroid belt represents not a planet destroyed, but a planet that never had the chance to be born at all. The reason traces back to the same swirling disk of dust and gas from which all the planets formed, and to one very large and very disruptive neighbor sitting just beyond the belt. Jupiter, the largest planet by far, was forming nearby during that same early era, and its enormous gravity reached out across a huge span of space, stirring and tugging at the smaller clumps of material, trying to gather together in the region we now call the belt. Instead of allowing those fragments to slowly collide and merge into ever larger bodies, the way material elsewhere in the disk managed to build up into planets, Jupiter's gravity kept nudging them into faster, more crossing orbits, so that when they did collide, they were often moving too quickly relative to one another to stick together. Rather than gently merging the way two raindrops might join into one larger drop sliding down a window, they would instead shatter or bounce apart, like marbles struck hard against one another, rather than settling softly into a pile. Over and over, across millions of years, this happened, and the result was a region caught in a kind of standstill, full of leftover building blocks that kept breaking each other down almost as quickly as they tried to build each other up. Jupiter, in effect, spoiled the recipe before the cake could ever finish baking, and the ingredients have simply been sitting there, largely unchanged, for 4.5 billion years. That, in a strange way, is what makes asteroids so scientifically valuable, despite how unassuming they look. Because they never became part of a larger planet, they were never melted down, mixed, and reprocessed the way material inside Earth or Venus or Mars eventually was, folded again and again into new rock through volcanic and geological activity. Many asteroids are instead something closer to fossils, chemically almost unchanged since the earliest days of the solar system, preserving in their stony or metallic material a kind of frozen snapshot of the ingredients the planets themselves were built from. When small pieces of these asteroids happen to be knocked loose through gentle collisions or gravitational nudges, and eventually find their way to Earth as meteorites, streaking briefly across the night sky before landing somewhere in a field or a desert or, occasionally, someone's back garden, scientists are able to study them in laboratories in ways no telescope allows, examining their chemistry atom by atom. Some meteorites even contain tiny mineral grains that formed before our sun existed at all, drifting into the solar nebula from some entirely different, older star. From this quiet, rubble-strewn gap, then, our slow drift outward carries us at last toward the giants, the first and largest of which waits just beyond, gathering more of the solar system's leftover material into its gravity than every other planet combined. Jupiter is so large that describing it accurately almost sounds like exaggeration, even when the numbers are stated plainly and without embellishment. If you gathered together every other planet in the solar system, all 7 of them, and pressed their combined mass into a single body, Jupiter would still outweigh that body by more than 2 to 1. Earth, by comparison, could fit inside Jupiter roughly 1,300 times over, and even that comparison undersells things, because Jupiter is not solid rock the way Earth is. There is no surface to stand on, no place where gas ends and ground begins. Instead, Jupiter is a planet built almost entirely from hydrogen and helium, the same 2 elements that make up the vast majority of the Sun itself, layered so deep and compressed so thoroughly by their own weight that the outer layers of gas gradually thicken into something more like a liquid, and further down still, under pressures difficult to fully imagine, that liquid hydrogen is squeezed into a strange metallic state capable of conducting electricity, something like the inside of a battery on a planetary scale. At the very center, there may be a core of heavier material, rock and metal, compressed far beyond anything achievable in a laboratory on Earth, though exactly how large or how solid that core is remains something scientists are still working out, using subtle measurements of how Jupiter's gravity tugs, ever so slightly unevenly, on passing spacecraft. What you actually see, looking at Jupiter through a telescope or in a photograph, is not this deep interior at all, but only the very topmost layer of clouds, a thin skin of visible atmosphere, wrapped around an immense body of gas underneath. And what a skin it is! Jupiter's clouds form into distinct, parallel bands that circle the entire planet, alternating between lighter zones and darker belts, running east to west with a crispness that almost looks painted on, almost too regular to be natural. This regularity comes from Jupiter's extraordinarily fast rotation. Despite being the largest planet by far, Jupiter spins on its axis in under 10 hours, faster than any other planet in the solar system, which means that a point on its equator is moving through space at tremendous speed. This rapid spin stretches the planet's weather patterns into these long, thin, encircling bands rather than the more chaotic, swirling patterns you might expect from a slower-turning world. The lighter zones are regions where gas rises upward, cooling as it climbs, and forming pale clouds, likely made largely of ammonia crystals, while the darker belts are regions where gas sinks back downward, warming slightly as it descends, revealing deeper, more colored layers of atmosphere underneath. It is, in a sense, an enormous and endless weather system, one without oceans or continents to disrupt it, driven instead purely by the planet's internal heat and its rapid rotation, spinning these bands around the entire globe in a pattern that has remained recognizably similar for as long as telescopes have been good enough to see it. Within and between these bands, storms churn constantly, some small and short-lived, others so large and long-lasting they seem to belong to an entirely different category of weather altogether. The most famous of these is the Great Red Spot, a storm so large that it could comfortably swallow the entire Earth, with room to spare, and possibly has been swirling in Jupiter's southern hemisphere for at least a few hundred years, since it was first noted by early telescope observers, and quite possibly longer than that. It is, in essence, an enormous high-pressure anticyclone, a mass of gas rotating counterclockwise, its reddish color likely coming from chemical compounds lifted up from deeper in the atmosphere and altered by sunlight, though the precise chemistry responsible for that particular shade of rust and brick red is still debated among scientists studying it. What is worth noticing, lying here in the dark and picturing it, is that the Great Red Spot has been slowly shrinking over the past century or so, its size measured carefully across generations of astronomers, and no one is entirely certain whether it will continue shrinking until it eventually vanishes, stabilize at some smaller size, or behave in some way not yet anticipated. It is a reminder that even something as seemingly permanent and iconic as a storm large enough to be seen from Earth through a modest telescope is still, ultimately, weather, still subject to change over long stretches of time, even if that change unfolds far too slowly for any single human observation to notice it happening. Beneath and around all of this visible weather, Jupiter generates a magnetic field unlike anything else in the solar system, a field so vast and so strong that it dwarfs Earth's own by a wide margin. This magnetism comes from that deep layer of metallic hydrogen mentioned earlier, swirling and conducting electricity far below the visible clouds, generating a magnetic field that extends outward from the planet in an invisible bubble so enormous that, if it could somehow be made visible in Earth's night sky, it would appear larger than the full moon, despite Jupiter's much greater distance. This magnetic bubble, called a magnetosphere, traps charged particles streaming outward from the sun, along with particles blasted into space by volcanic activity on one of Jupiter's moons, and channels them into intense radiation belts that circle the planet, belts so powerful that spacecraft passing through them must be carefully shielded to avoid having their electronics damaged during a flyby. It is an environment far harsher, in its own way, than anything on the sunlit, cloud-topped surface visible from a telescope might suggest. And then there are Jupiter's rings, thin and faint enough that they went entirely unnoticed until spacecraft finally passed close enough to detect them directly, a striking contrast to Saturn's dramatically visible ring system, which has been recognizable through even simple telescopes for centuries. Jupiter's rings are made not of ice, as much of Saturn's rings are, but of fine, dark dust, likely kicked up from small nearby moons through tiny meteoroid impacts over long stretches of time, drifting into orbit around the planet in delicate, nearly invisible sheets. They are a quiet reminder that ring systems themselves are not unique to Saturn, but seem to form, in one way or another, around several of the giant planets, differing mainly in how much material happens to be available nearby and how visible that material becomes as a result. It is Jupiter's moons, though, more than its rings, that reward the slowest and closest attention, because among them are worlds startlingly different from one another, despite orbiting the very same planet. Io, the innermost of the 4 largest moons, is the most volcanically active body known anywhere in the solar system, its surface constantly resurfaced by eruptions driven by the immense gravitational squeezing it experiences from Jupiter and from its neighboring moons, a process called tidal flexing, which heats Io's interior the way repeatedly bending a wire back and forth heats the metal at the bend. Europa, just beyond Io, presents an almost entirely opposite kind of world. Its surface, a smooth, cracked shell of ice, beneath which many scientists believe an ocean of liquid water may exist, kept from freezing solid by that same tidal flexing, warmed gently and continuously by Jupiter's gravitational grip. Ganymede, larger than the planet Mercury, is the largest moon in the entire solar system, and remarkably, generates its own magnetic field, something otherwise unheard of among moons. And Callisto, the outermost of these 4, is an ancient, heavily cratered world, its surface so thoroughly scarred by billions of years of impacts that it appears to have changed relatively little since the earliest days of the solar system, a quiet, undisturbed record of just how much debris was still flying around in those first violent chapters of planetary formation. 4 moons, then, circling one planet, and yet volcanic fire, hidden ocean, its own magnetism, and frozen ancient stillness, each entirely distinct from the others, as though Jupiter had gathered, in miniature, some of the solar system's greatest variety into a single orbiting family. From here, drifting a little further outward still, we come to a planet almost as large, wrapped in rings far more magnificent and far easier to see. Let your breathing settle a little further, because now we drift outward, past Jupiter's crowded family of moons, past a long stretch of quiet dark, until a soft, pale gold light begins to resolve into rings, wide, flat, impossibly thin, wrapped around a planet that seems, at first glance, almost too perfect to be real. This is Saturn, and it has fascinated observers since Galileo first turned his imperfect telescope toward it in 1610 and saw something he could not quite explain, describing it, in his confusion, as a planet with ears, 2 strange bulges on either side that would not resolve into any shape he recognized. It would take decades, and better telescopes, and the careful, patient eye of the astronomer Christian Huygens, before anyone understood that what Galileo had seen was a ring, a thin, encircling structure unlike anything else known in the sky. Saturn itself is a giant world of gas, smaller than Jupiter but still enormous, wide enough to swallow more than 700 Earths within its volume. And yet, despite this size, Saturn holds a peculiar distinction among all the planets. It is the least dense of them, made up so predominantly of light hydrogen and helium, so loosely packed together, that if you could somehow find an ocean vast enough to hold it, Saturn would float. This is not a metaphor, not an exaggeration meant to impress you before sleep, but a simple consequence of its composition, a planet built mostly from the two lightest elements in the universe, compressed only loosely by its own modest gravity compared to Jupiter's crushing grip. Picture a beach ball, not a bowling ball, and you have a better sense of what Saturn is actually like beneath its golden haze, however strange that image might feel applied to something 95 times the mass of Earth. That golden haze is itself worth lingering on, because Saturn's atmosphere, while it moves with tremendous violence beneath the surface we can see, presents to our eyes a much calmer, more muted face than Jupiter's turbulent stripes. The winds here are, in fact, the fastest recorded anywhere in the solar system, gusting in Saturn's equatorial regions at speeds exceeding 1,000 miles per hour, fast enough to carry a storm entirely around the planet in a matter of days. And yet, the visible bands of color are softer, more pastel, more butterscotch than Jupiter's bold rust and cream, largely because a high layer of haze sits above the deeper clouds, diffusing and gentling the colors, the way a thin fog softens the edges of streetlights on a cold night. Every so often, roughly once every Saturnian year, which is to say, roughly every 30 of our own years, a truly enormous storm erupts in Saturn's northern hemisphere, a churning white blemish large enough to wrap entirely around the planet, visible even to Earth-based telescopes, before it eventually fades and the atmosphere settles back into its usual quiet drift. And near Saturn's North Pole sits one of the strangest weather features known anywhere, a persistent, six-sided jet stream, a hexagon of wind wide enough to hold several Earths within it, its perfectly geometric shape still not fully explained, though laboratory experiments with spinning fluids have managed to reproduce something similar, suggesting it may simply be what happens naturally when a fast jet stream circles a rotating pole under just the right conditions. But it is the rings, of course, that anyone drifting toward sleep tonight is likely picturing, and they deserve every bit of the wonder they receive, even once you understand what they actually are. They are not solid, not a single continuous sheet of matter as they might first appear from a distance, but an almost unimaginably vast collection of individual particles, ranging from grains as fine as dust up to house-sized chunks of ice, each one independently orbiting Saturn according to its own distance, the way each fish in a school follows the current while still moving on its own. Most of this material is water ice, remarkably bright and clean, which is part of why the rings reflect sunlight so beautifully, and the ring system as a whole, though it stretches out to a diameter that could comfortably span the distance between the Earth and the Moon several times over, is astonishingly thin, in most places no more than about 30 feet from top to bottom. If you shrank Saturn down to the size of a large dinner plate, its rings would be thinner than a sheet of paper laid across it, a proportion so extreme that it can be hard to hold in the mind even once you know the numbers. The rings are not smooth either, but divided into distinct bands separated by gaps, the most famous of which is called the Cassini division, a dark space named for the Italian astronomer Giovanni Cassini, who first noticed it in 1675 while carefully observing Saturn through a telescope from Paris. These gaps exist largely because of small moons embedded within or orbiting near the rings, sometimes called shepherd moons, whose gravity nudges nearby ring particles into cleared lanes, the same way a sheepdog moves along the edge of a flock, keeping the animals within it loosely herded into a defined shape, rather than a shapeless sprawl. Two small moons named Pandora and Prometheus perform exactly this function for one of Saturn's thin outer rings, one orbiting just inside it and one just outside, their combined gravitational tug keeping that ring's edges crisp and narrow, rather than allowing it to spread out and disperse over time. It is a small, quiet kind of architecture, invisible and unplanned, and yet remarkably effective, sustained for who knows how many millions of years by nothing more than the patient, repeated pull of gravity. And then there are Saturn's larger moons, more than 80 confirmed in total, though 2 in particular deserve to be lingered over before we drift on. Titan, the largest of them, is in some ways the most Earth-like body anywhere else in the solar system. Not in temperature, certainly, since it sits at a bitterly cold average of nearly -300 degrees Fahrenheit, but in the presence of a thick atmosphere, thicker even than our own, and in the existence of lakes and rivers and rain, though made not of water but of liquid methane and ethane, chemicals that on Earth we know only as gases. Picture a quiet lakeshore at dusk, the kind of scene that might exist in a gentle dream, and then imagine that same shoreline, lit by a dim orange sky, its lake filled not with water, but with something closer to what we burn in stoves, cold enough that it stays liquid only because Titan itself is so far from the sun's warmth. The spacecraft Huygens, released from the Cassini orbiter, actually landed on Titan's surface in January of 2005, sending back images of a landscape carved by flowing liquid, rounded stones scattered across a floodplain, evidence of an active, weather-driven world entirely unlike our own in its chemistry, yet strangely familiar in its shapes. Enceladus, much smaller than Titan, holds its own quiet surprise. Beneath a bright, icy crust, warmed again by that same tidal flexing we encountered at Jupiter's moons, Enceladus appears to hold a liquid ocean of salty water, and remarkably, that ocean occasionally vents itself into space, erupting through cracks near the moon's south pole in plumes of ice crystals that the Cassini spacecraft flew directly through, sampling water from another world's ocean simply by passing through the spray. It is a small, cold moon, quietly leaking evidence of what lies hidden inside it, out into the vacuum above, for anything patient enough to be listening. From here, having lingered long enough among Saturn's rings and moons, we can let ourselves be carried further outward still, toward a planet tipped strangely on its side, spinning through the dark in a way unlike anything we have encountered yet. Uranus moves through space in a way that still puzzles anyone who first learns about it. Every other planet we have visited so far spins more or less upright, like a top standing on a table, tilted a little this way or that, but basically vertical as it circles the sun. Uranus does not do this. Uranus lies almost completely on its side, tipped over by about 98 degrees, so that instead of spinning like a top, it rolls through its orbit like a ball, or perhaps more like a wheel rolling along a track, its poles pointing not up and down, but nearly directly at the sun, and directly away from it in turn. Imagine the Earth tipped so far over that the North Pole sometimes faced the sun almost directly overhead, while half a Uranian year later, that same pole would be pointing into the blackness of deep space, having not seen sunlight in decades. That is roughly what happens on Uranus, where a single season can last more than 20 years, and where one pole endures a summer of continuous daylight for decades at a time, while the opposite pole sits in an equally long, equally dark winter. No one knows for certain why Uranus ended up this way. The leading idea, and it remains an idea rather than a settled fact, is that sometime very early in the solar system's history, while the planets were still forming and the neighborhood was crowded with debris, something enormous, perhaps an object the size of Earth or larger, struck Uranus with tremendous force and knocked it over, the way a hard enough collision might tip a spinning gyroscope onto its side rather than merely wobbling it. Other explanations have been proposed too, involving the gravitational pulls of large moons forming and shifting over long stretches of time, but the single dramatic collision remains, at least for now, the picture many scientists find most persuasive. Whatever the true cause, the result is a planet that experiences its days and nights, its seasons and its slow orbital rhythm, in an orientation unlike anything else we have encountered on this journey outward from the Sun. Uranus itself was discovered relatively recently in the story of astronomy, in 1781, by William Herschel, a German-born musician living in England who had taken up telescope building and stargazing as a passionate hobby alongside his work as a composer and performer. Herschel was not even looking for a new planet on the night he found it. He was surveying the sky methodically, cataloging stars, when he noticed an object that did not look quite like the pinpoint of light a star should be. It appeared instead as a small, faint disk, and when he tracked its position over successive nights, he found that it moved against the background stars, the telltale sign of something within our own solar system rather than a distant sun. At first, Herschel assumed he had found a comet, since comets were the more familiar sort of moving object. But as astronomers across Europe calculated its orbit in the months that followed, it became clear that this was something else entirely, a new planet, the first one discovered in recorded human history rather than known since antiquity. It had, in effect, been hiding in plain sight, visible even to the naked eye under sufficiently dark skies for anyone who happened to look at exactly the right point and know what they were seeing. Yet it took the patient, systematic sweep of a telescope and an astronomer curious enough to double-check anything unusual before anyone actually noticed it for what it was. Like Jupiter and Saturn, Uranus has no solid surface to land on, but its interior is built quite differently from either of the two giant planets we have already visited. Where Jupiter and Saturn are made mostly of hydrogen and helium gas compressed down into deep, layered atmospheres, Uranus and its neighbor Neptune belong to a different category that scientists sometimes call ice giants. This name can be a little misleading, since it does not mean these planets are covered in ice the way a winter pond might be. Instead, it refers to the mix of materials thought to make up much of their interior, which likely consists of a thick, slushy layer of water, ammonia, and methane compounds, all mixed together under such extraordinary pressure and heat that they behave less like the ice we know and more like a dense, hot, electrically conductive fluid, sometimes called a supercritical fluid, that does not resemble familiar water or ice at all, despite sharing some of the same basic chemical ingredients. Deeper still, there may be a smaller rocky core, though much about the exact structure remains genuinely uncertain, since no spacecraft has ever probed beneath the visible cloud tops of either ice giant, and much of what scientists infer comes from models, from careful measurements of gravity and magnetic fields, and from comparisons with what is better understood about Jupiter and Saturn. The outer atmosphere of Uranus appears from a distance as a nearly featureless pale blue-green, a soft, muted color that comes from methane gas in the upper atmosphere, absorbing red light from sunlight and reflecting the blue and green wavelengths back out toward any observer, in much the same way that certain gases in Earth's atmosphere shape the particular blue of our own sky. Beneath that calm-looking surface, however, winds do blow, some of them among the fastest recorded anywhere in the solar system, reaching several hundred miles per hour in places, driven by the planet's rotation and by heat escaping from somewhere within, even though Uranus radiates remarkably little internal heat compared to Jupiter, Saturn, or its neighbor Neptune. This is another small mystery, tucked inside the planet's list of unusual traits, since something is generating those winds despite Uranus behaving, thermally, as though it were unusually quiet and cold on the inside for a planet its size. Uranus, like the other giants we have visited, has rings, though they are far fainter and darker than Saturn's famous bright bands, made of particles that reflect very little light, so dark in fact that they went entirely unnoticed by human eyes and telescopes for centuries after the planet itself was discovered. They were finally found in 1977, not by a spacecraft flying past and photographing them directly, but through a clever bit of detective work performed by astronomers watching Uranus pass in front of a distant star. As the planet's disk approached the star's light dimmed and brightened repeatedly in a peculiar pattern, both before Uranus fully covered it and again after it had passed by, a signature that made sense only if a series of narrow, dark rings surrounded the planet and were briefly blocking the star's light each time one of them passed across it. It was an elegant piece of reasoning, deducing the presence of rings not by seeing them directly, but by watching starlight blink in a pattern that only rings could explain. Uranus also carries a retinue of moons, 27 confirmed so far, most of them named not for figures out of Greek or Roman mythology, as is the custom for nearly everything else in the solar system, but for characters drawn from the plays of William Shakespeare and the poetry of Alexander Pope, a naming tradition begun by Herschel's own son, John, and continued ever since. Moons called Titania, Oberon, Miranda, Ariel, and Umbriel drift around this sideways planet, some of them showing surfaces scarred by canyons deep enough to make the Grand Canyon look modest by comparison, hinting at violent geological histories that scientists are still working to fully understand. And now, having circled this strange, tilted world with its faint rings and its literary moons, we can turn our attention to the very edge of the traditionally recognized planets, to a deep blue world discovered not by patient searching of the sky alone, but by careful mathematics, predicting almost exactly where it ought to be found before anyone ever pointed a telescope in its direction. Beyond that deep blue world, the solar system does not simply stop, the way a story might end at the last page of a book. It thins out instead, gradually, into a vast and shadowed region that astronomers call the Kuiper Belt, a great ring of icy debris left over from the earliest days of planet formation, circling the Sun far past the orbit of Neptune. Think of it as construction scraps that were never quite cleaned up. When the planets were assembling themselves nearly 4.5 billion years ago out of a swirling disk of gas and dust and rubble, most of the material, close to the Sun, eventually got gathered into the 8 major worlds, or fell into the Sun itself, or was flung out of the system entirely by gravitational encounters. But far out at the edges, where the disk was thin and cold and the gravity of any single body was too weak to gather much of anything efficiently, countless smaller objects were left drifting, never quite pulled together into planets, never quite scattered away either. They have been circling out there, largely undisturbed, ever since. The idea of such a belt existing was proposed by several astronomers across the 20th century, though it is most often associated with Gerard Kuiper, a Dutch-American astronomer who, in 1951, suggested that a disk of small, icy bodies might once have existed beyond Neptune, left over from the solar system's formation. Curiously, Kuiper himself thought that by the present day, such a disk would likely have been cleared away or absorbed, so in a sense, he predicted the very thing he did not expect anyone would still find. It took until 1992 for astronomers David Jewitt and Jane Liu, after years of patient searching with a telescope in Hawaii, to actually spot one of these distant objects, a small icy body given the unglamorous name 1992 QB1. It was the first confirmed proof that the belt Kuiper had once speculated about really was still out there, largely intact, a frozen museum of the solar system's infancy. It was within this same distant region, decades earlier, that one particular object had already been found, though nobody at the time understood quite what it was part of. In 1930, a young astronomer named Clyde Tombaugh, working at Lowell Observatory in Flagstaff, Arizona, was tasked with a painstaking search for a hypothetical ninth planet, one that the observatory's founder, Percival Lowell, believed must exist to explain small irregularities in the orbit of Neptune. Tombaugh spent months comparing photographic plates of the night sky taken days apart, using a device called a blink comparator that let him flip rapidly between two images of the same star field, watching for anything that shifted position against the fixed background of stars, the way a planet would, but a distant star would not. On the 18th of February that year, after examining plates taken in January, he found exactly such a shifting point of light. It was Pluto. Ironically, the very irregularities in Neptune's orbit that had prompted the search turned out to be based on a mistaken estimate of Neptune's mass, and Pluto itself, as later measurements would reveal, was far too small and too light to have caused any such wobble at all. Tombaugh had found something real, but not for the reason anyone had gone looking for it. For decades, Pluto stood as the ninth planet, small and mysterious, so far away that even the best telescopes on Earth could resolve little more than a faint, fuzzy dot. In 1978, an astronomer named James Christie, studying photographic plates of Pluto at the United States Naval Observatory, noticed something odd, a slight bulge on one side of Pluto's image that appeared and disappeared over time. That bulge turned out to be a moon, later named Charon, so large relative to Pluto itself, roughly half its diameter, that the two bodies actually orbit a shared point of balance located outside Pluto entirely, more like a pair of dancers spinning around a point between them than a planet with a moon obediently circling it. Pluto, it turned out, was not traveling alone. As astronomers continued searching the outer solar system through the late 20th and early 21st centuries, they began finding more objects out in the Kuiper Belt, some of them substantial in size. In 2005, an astronomer named Mike Brown and his colleagues discovered a body, later named Eris, that appeared for a time to be even larger than Pluto itself. This discovery forced a question that astronomers had been quietly avoiding for years, namely, what exactly counts as a planet? And if Eris deserved the title, shouldn't there now be 10 planets, or more, as further large Kuiper Belt objects were surely waiting to be found? In 2006, the International Astronomical Union settled the matter, at least officially, by adopting a formal definition of a planet, one that required a body not only to orbit the Sun and be rounded by its own gravity, but also to have cleared its orbital neighborhood of other debris. Pluto, sharing its region of space with countless other icy bodies in the Kuiper Belt, did not meet that third criterion. It was reclassified as a dwarf planet, a decision that proved unexpectedly controversial, generating genuine public affection and protest on Pluto's behalf, the kind of reaction rarely stirred by a change in astronomical bookkeeping. Whatever one calls it, Pluto turned out to be a far richer and stranger place than anyone expected when, in 2015, the New Horizons spacecraft, after a journey of nearly a decade, flew past it and sent back the first close images humanity had ever seen of its surface. Rather than a dead, featureless ball of ice, Pluto revealed mountains of solid water ice, some rising as high as the Rocky Mountains, a thin, hazy blue atmosphere, and a vast, smooth plain of frozen nitrogen, shaped remarkably like a heart, later named Tombaugh Regio, in honor of the man who had found the little world 85 years earlier. Some scientists now suspect that beneath that icy heart may lie a liquid ocean of water, kept from freezing solid by heat trapped within Pluto's rocky core, a possibility that, if confirmed, would place Pluto among a surprising number of icy worlds in the outer solar system suspected of hiding oceans beneath their frozen shells. Pluto shares its dwarf planet status with several other worlds, each strange in its own way. Eris, still one of the most massive known objects in the Kuiper Belt, takes over 500 years to complete a single orbit of the Sun. Haumea spins so rapidly, once every 4 hours, that it has been stretched by its own rotation into an elongated egg-like shape, and astronomers have even detected a thin ring circling it, an unexpected feature for so small and distant a body. Makemake, named after a creator deity of the Rapa Nui people of Easter Island, drifts along nearby, its surface coated in frozen methane. And closer to home, in the asteroid belt between Mars and Jupiter, sits Ceres, the largest object there, also classified as a dwarf planet, and visited by NASA's Dawn spacecraft, which found bright patches on its surface, later identified as deposits of salt left behind when subsurface water evaporated into the vacuum of space. Scattered among and beyond these worlds drift the comets, perhaps the most ancient and unaltered fragments of all, often described, in a phrase coined by the astronomer Fred Whipple in the 1950s, as dirty snowballs, loose mixtures of ice, dust, and rock that have remained largely unchanged since the solar system's birth. Some comets, with relatively short orbital periods, are thought to originate in the Kuiper Belt itself. Others, arriving on orbits so long they take thousands or even millions of years to complete, are believed to come from a far more distant and enormous spherical shell of icy bodies called the Oort cloud, a region first proposed by the Dutch astronomer Jan Oort in 1950 and thought to extend nearly a quarter of the way to the nearest other star. When a comet does swing in toward the Sun, solar heat begins to vaporize its ices, releasing gas and dust that form the glowing tails we sometimes see stretched across the night sky, always pointing away from the Sun, pushed outward by sunlight and the solar wind, regardless of which direction the comet itself happens to be traveling. Halley's Comet, perhaps the most famous of these visitors, returns roughly every 76 years, its passages recorded by human observers for more than 2,000 years, including its appearance stitched into the Bayeux Tapestry in the year 1066. And it is out past even the farthest reaches of that Oort cloud, at the true, uncertain, whisper-thin boundary where the Sun's influence finally gives way to the vast darkness between stars, that our slow journey through this solar system must eventually arrive. But before we can speak of that boundary with any real understanding, it helps to slow down and consider what actually holds this whole arrangement together, because nothing out there is tied down by rope or scaffolding. There is no visible architecture to the solar system, no lines drawn in space marking where one planet's territory ends and another's begins. What holds everything in its place is a kind of endless falling, a permanent compromise between motion and gravity that took human beings a remarkably long time to understand correctly. Picture a ball thrown from a hilltop. If you throw it gently, it arcs downward and lands close by. Throw it harder, and it travels farther before gravity pulls it to the ground. Now imagine throwing it hard enough that as it falls, the curve of its path matches the curve of the Earth falling away beneath it. The ball would never land. It would simply keep falling, forever missing the ground, circling the planet in what we call orbit. This was the insight Isaac Newton described in the late 1600s, sometimes illustrated with his own thought experiment of a cannon fired from a very tall mountain. An orbit, in this sense, is not an escape from gravity. It is a continuous surrender to it, precisely balanced by forward motion. The moon is falling toward the Earth right now, and has been for over 4 billion years, and will keep falling for billions more, always missing. The planets are doing the same thing around the sun, each at a speed exactly suited to the pull it feels at its particular distance. Mercury, tucked in close where the sun's gravity is fierce, has to move at a blistering pace, nearly 47 kilometers every second, just to keep from spiraling inward. Neptune, out in the cold and dark, moves at a comparatively leisurely 5 kilometers per second, because the sun's grip that far away has grown so much weaker that a gentler pace is enough to keep it falling in its wide, unhurried circle. This relationship between distance and orbital speed was worked out with startling precision by the German astronomer Johannes Kepler in the early 1600s, using decades of naked-eye observations recorded by his mentor, Tycho Brahe. Kepler found that planets do not move in perfect circles at all, but in slightly stretched ovals called ellipses, with the sun sitting not quite at the center, but off to one side, at a point mathematicians call a focus. He found, too, that a planet moves faster when it swings closer to the sun and slower when it drifts farther away, sweeping out equal areas of space in equal times, like a skater pulling in her arms to spin faster and extending them to slow down. Gravity, though, is not only about the sun and a single planet politely orbiting it. Every object in the solar system pulls on every other object, all at once, all the time, in a tangle of mutual attraction that never fully resolves into simplicity. Most of these extra tugs are so faint they barely matter, but every so often, two orbital periods line up in a way that amplifies rather than cancels out, and the result is called a resonance. Consider Pluto, whose orbit actually crosses inside Neptune's path around the Sun. It might seem like a collision should eventually be inevitable, but Pluto completes exactly 2 orbits for every 3 that Neptune completes. A neat 2 to 3 resonance that means the two bodies are never actually near each other when Pluto swings through, even though their paths overlap on paper. It is less like a shared lane on a highway and more like 2 dancers who never occupy the same square of floor at the same moment, because their steps are timed to avoid it. Resonances shape the solar system in quieter ways, too. Within the asteroid belt, there are specific distances from the Sun where almost no asteroids are found at all, gaps first noticed by the American astronomer Daniel Kirkwood in the 1860s and now called Kirkwood gaps. At those particular distances, an asteroid's orbital period would divide evenly into Jupiters, say exactly 1/3 or 2/5 of it, and the repeated, well-timed tugs from that giant planet, arriving at the same point in the asteroid's orbit again and again, gradually pump the asteroid's path into a new shape, sending it elsewhere. Jupiter, simply by being so enormous, quietly gardens the debris of the inner solar system this way, clearing certain lanes and crowding others, even from hundreds of millions of kilometers away. All of this, the falling moons, the elliptical paths, the timed dances of resonance, takes place within a bubble that the sun itself creates and maintains. It is easy to think of the sun's influence as ending wherever its light grows too dim to notice, but light is not the only thing streaming outward from that star. The sun is also constantly shedding a thin, hot wind of charged particles, mostly protons and electrons, blown outward from its outer atmosphere at speeds that can exceed 1,000,000 kilometers per hour. This solar wind was predicted on theoretical grounds by the physicist Eugene Parker in 1958, a proposal met with real skepticism at the time, since no one had detected any such thing, and it seems strange that a star's atmosphere would simply flow away into space rather than staying put. Parker turned out to be correct, and later spacecraft confirmed the wind's existence directly, its pressure detectable even in the way it deflects and shapes the tails of comets, always pointing away from the sun. just as we've heard. This outward wind inflates a vast, roughly teardrop-shaped bubble around the entire solar system called the heliosphere, and it is really this bubble, more than any particular planet or belt, that marks the practical edge of the Sun's territory. Inside the heliosphere, the solar wind dominates, pushing back the thin gas and cosmic rays that drift through the galaxy at large. But the wind does not blow forever. Far out past the orbit of Neptune, at a boundary called the heliopause, the pressure of the solar wind finally weakens to match the pressure of the interstellar medium pressing in from outside, and the two come to a kind of standoff. NASA's Voyager 1 spacecraft, launched in 1977, crossed this boundary in 2012, and its instruments registered the change distinctly: a sudden drop in particles streaming from the Sun, and a rise in particles arriving from elsewhere in the galaxy. Evidence that the little machine had, in a very real sense, left the Sun's bubble and entered the space between stars, even though by most other definitions, including the presence of the Oort cloud, it remains inside the solar system for a very long time yet. And this is really the strange, layered truth of it. The solar system does not have one single edge, but several, depending on what you choose to measure. There is the edge of planetary orbits, the edge of the Sun's steady wind, and then, further still, the edge of the Sun's gravitational reach, which stretches out to encompass that dim, distant shell of the Oort cloud, a boundary so unimaginably far that light from the Sun, after leaving its surface, would need well over a year of travel to reach it. It is a strange thought to hold on to as you drift toward sleep, that the quiet room around you sits inside a bubble of solar wind, itself inside a much larger bubble of solar gravity, and that even that outer boundary is not really an ending at all, but simply the place where our own star's quiet influence finally fades into whatever comes next. Long before any spacecraft could register the faint pressure of the solar wind, human beings were already tracking the planets by nothing more than patient eyes and a clear night. If you go back far enough, before telescopes, before written astronomy as we would recognize it, the planets were simply 5 bright points of light that behaved oddly. Stars held their positions relative to one another, forming the same fixed patterns night after night, but these 5 lights wandered against that backdrop, drifting slowly through the constellations over weeks and months. The ancient Greeks called them planetes, meaning wanderers, and the name has stuck with us for more than 2,000 years, even though we now know the wandering had nothing to do with any will of their own, and everything to do with the simple geometry of worlds orbiting a shared sun at different speeds. The Babylonians were tracking these wanderers with real rigor as early as the 2nd millennium BCE, keeping clay tablets full of careful observations of Venus, noting when it appeared in the morning sky and when it vanished into the evening glow, recording its comings and goings across generations of scribes. This was not idle curiosity. In many ancient cultures, the movements of the planets were tied to omens, to calendars, to the rhythms of planting and flooding, and so the incentive to watch closely and record faithfully was strong, sustained not by any one person's curiosity, but by institutions that outlasted individual lives. The Chinese imperial astronomers kept similarly meticulous records, as did astronomers in the Maya world, who built a sophisticated calendar system, partly around the movements of Venus, tracking its cycle with an accuracy that still impresses anyone who studies it today. None of these observers had any instrument beyond the naked eye, a horizon to measure against, and the discipline to keep watching, night after night, year after year, in an era when a cloudy week could mean losing the thread of a slow-moving pattern. For a long stretch of history, this naked-eye tradition produced an image of the cosmos, with the Earth sitting still at the center, and the sun, moon, and planets circling around it. This geocentric view, refined most famously by the Greek astronomer Ptolemy in the 2nd century, was not stupid or careless. It fit the observations reasonably well, once enough complicated adjustments were added, and it matched the simple, everyday sense that the ground beneath our feet does not seem to move. It would take more than 1,000 years, and the work of the Polish astronomer Nicolaus Copernicus in the 16th century, to seriously propose that the sun, not the earth, belonged at the center, with all the planets, Earth included, circling around it. Copernicus published his ideas cautiously near the end of his life, aware of how disruptive they might seem, and for decades afterward the debate continued, argued over with geometry and observation rather than settled by any single decisive moment. The decisive moment, or at least the one that shifted the balance most dramatically, came in 1609 and 1610, when the Italian scientist Galileo Galilei turned a new invention, the telescope, toward the sky. Telescopes had existed for practical uses, like surveying and warfare, just before this, but Galileo was among the first to point one upward and take what he saw seriously as evidence. What he found dismantled the old picture piece by piece. He saw that the moon was not a smooth, perfect sphere, but a rough, cratered world with mountains and shadowed valleys, unsettlingly similar to the earth beneath his own feet. He saw 4 small points of light circling Jupiter, changing position from night to night, and eventually realized they were moons, tiny worlds orbiting another planet rather than the Earth, which meant that at least one center of motion existed elsewhere in the sky, and he saw Venus pass through a full set of phases, much like the moon does, a pattern that only made sense if Venus orbited the sun and not the Earth. Each of these observations, made through a device barely more powerful than a modern pair of binoculars, chipped away at centuries of settled belief, and Galileo paid a real price for saying so plainly what his eyes had shown him. From there, the pace of discovery slowed to something more incremental, but no less patient. Astronomers built larger telescopes, ground finer lenses, and polished larger mirrors, each improvement revealing details that had simply been invisible before. In 1781, an amateur astronomer in England named William Herschel, using a telescope he had built himself, noticed an object that did not behave like a star. It moved, slowly, against the background sky, and after careful tracking it became clear this was not a comet, as he first suspected, but an entirely new planet, one that had been sitting in plain view for all of recorded history, without anyone recognizing it for what it was. Herschel had discovered Uranus, doubling, in a sense, the known size of the solar system overnight, and he did it with a homemade telescope in his own backyard, working alongside his sister Caroline, who became a formidable astronomer in her own right. Neptune's discovery, some 65 years later, came about in a stranger and in some ways more remarkable way. Astronomers had noticed that Uranus was not orbiting quite as the mathematics predicted, tugging slightly out of place, and some suspected an unseen planet beyond it was responsible for the pull. Working from these tiny irregularities, the French mathematician Urbain Le Verrier calculated where such a planet ought to be, using nothing but pen, paper, and Newton's laws of gravity, and sent his prediction to an observatory in Berlin. On the very night astronomer Johann Galle received the letter, in 1846, he pointed his telescope to the predicted spot and found Neptune sitting almost exactly there, a planet discovered not by a lucky glance through an eyepiece, but by careful arithmetic, confirmed afterward by a single night of looking. For more than a century after that, telescopes on the ground, and eventually in orbit, remained our only way of studying the planets, watching from a great distance as light gathered slowly on photographic plates and, later, electronic sensors. That changed in the second half of the 20th century, when human beings began sending machines out to visit these worlds directly. Robotic spacecraft flew past Venus and Mars in the 1960s, and the Soviet Venera landers, remarkably, managed to survive the crushing pressure and furnace heat of the Venusian surface long enough to send back a handful of images before failing. Brief postcards from one of the most hostile places any human instrument has ever touched down. American Viking landers reached Mars in 1976, settling onto its rusty plains and scooping its soil in a careful search for any sign of life, a search that returned results ambiguous enough to still be debated today. But of all these missions, it is perhaps the twin Voyager spacecraft, launched in 1977, that carry the story furthest and most poignantly. Engineers realized that a rare alignment of the outer planets would allow a single spacecraft to visit several of them in sequence, using each planet's gravity to fling it onward toward the next, a maneuver so elegant it is sometimes called a grand tour, and this alignment would not repeat for another 175 years. Voyager 2 swept past Jupiter, then Saturn, then Uranus, then Neptune, sending back the first close images of ice giants that had previously existed to us only as faint points of light, while Voyager 1 captured extraordinary views of Jupiter's storms and Saturn's rings before angling upward, out of the plane of the planets entirely. Each spacecraft carried a golden record, a phonograph disc etched with sounds and images of Earth, greetings in dozens of languages, whale songs, a baby's cry, included not because anyone truly expected it to be found, but as a quiet, hopeful gesture, a message in a bottle cast into a very large ocean by people who understood they would likely not be alive to know if it ever mattered. Both spacecraft are still out there tonight, still moving, still sending back faint whispers of radio signal that take more than 20 hours to reach the antennas built to listen for them. In 1990, as Voyager 1 was leaving the family of planets behind for good, a scientist working on the mission asked that its camera be turned around one last time, back toward the world it had come from. The image that resulted showed nothing dramatic, just a scattering of light through the camera's optics, and, within one of those pale bands of scattered sunlight, a single pixel, less than the width of a period on this page, holding the entire Earth. Every person who had ever lived, every argument and every kindness, every war and every wedding, contained in that one mote of light suspended in a sunbeam. It became known as the pale blue dot, and it remains one of the strangest kinds of photograph a human being has ever taken, a picture of home made valuable precisely by how little of it you can see. Voyager 1 crossed into interstellar space in 2012, the first human-made object to do so, passing beyond the boundary where the outward pressure of particles streaming from our sun finally gives way to the thinner, colder material drifting between stars. It is still technically inside the sun's gravitational influence, still bound loosely to our star by the same invisible thread that holds the planets in their paths, and it will remain so for tens of thousands of years yet, moving through the Oort cloud's distant reaches long after its instruments have gone silent and its golden record has become the only thing left that speaks. But in every practical sense, it has already left. It has passed beyond the last of what we might comfortably call ours, and out into the shared dark that belongs to no one. It is a strange thing to sit with, the idea that a small assembly of metal and wire, built by hands not so different from your own, is out there right now, further from home than anything else we have ever made, carrying pictures of children and diagrams of DNA, and the sound of a mother kissing her infant, moving through a silence so complete that the concept of up or down no longer applies. And it is perhaps stranger still to realize that you, too, are moving, right now, at this very moment, just as surely as that distant spacecraft, even though everything around you feels perfectly, reassuringly still. You are sitting or lying in a particular room, in a particular building, on a particular patch of ground, and none of that ground is holding still. The earth beneath you is turning at roughly 1,000 miles an hour at the equator, slower the further you are from it, carrying you sideways through the night, without the faintest sensation of motion, the same way a boat can glide across smooth water, so gently that only the changing shoreline gives away the fact that you are moving at all. At the same time, the Earth is racing around the Sun at about 67,000 miles an hour, tracing that great ellipse we spoke of earlier, an orbit so vast that it takes a full year to complete even at that tremendous speed. And the Sun itself, the star that anchors all of this, that every planet and moon and asteroid and comet quietly obeys, is not fixed in place either. It is moving too, carrying the entire solar system along with it, the way a single leaf floating on a river moves with the current even as it seems, from its own small vantage point, to simply be sitting on the surface of the water. The Sun orbits the center of the Milky Way galaxy, and it does so at an extraordinary pace, something in the neighborhood of 500,000 miles an hour, fast enough to cross the distance from here to the Moon in about 30 minutes. And yet, because the distances involved are so staggeringly large, because the center of the galaxy lies some 26,000 light-years away, this tremendous speed still only completes a single full orbit once every 225 to 250 million years, an interval so long that the last time our Sun was in this particular position, relative to the galaxy's core, dinosaurs had not yet appeared on Earth, and the continents themselves were arranged into shapes we would not recognize. We are, each of us, riding on a planet, orbiting a star, that is itself slowly circling the bright, crowded hub of a vast pinwheel of some 200 billion other stars, most of which likely have planets of their own, worlds we will never see, circling suns, whose light left them so long ago that by the time it reaches your eyes on a clear night, the star that sent it may have already changed, or dimmed, or in some cases quietly gone out. And the Milky Way itself is not standing still either. It is drifting through the wider darkness alongside its neighbors, tugged gently by the gravity of other galaxies nearby, part of a small cluster of galaxies that is itself part of a much larger structure, a vast web of galactic clusters strung together across billions of light-years like dew caught on a spider's web stretched impossibly wide. There is, as far as anyone has been able to determine, no true center to any of it, no fixed point from which everything else can be measured, only motion within motion within motion, each layer carrying the next, the way a child asleep in the back seat of a car is carried along a highway without ever knowing which direction is forward. It can feel dizzying to hold all of that at once, the turning Earth, the racing orbit, the drifting Sun, the slow wheel of the galaxy, layers of movement stacked so deep that none of them can be felt directly, all of them arriving at your body only as the gentle, ordinary fact of a night settling in, a temperature dropping by a degree or two, a sky slowly filling with stars, whose light set out on its journey long before you were born. But perhaps it does not need to feel dizzying. Perhaps it can simply feel like what it is, which is a kind of enormous, quiet reassurance, the knowledge that you are held, gently and continuously, by forces so much larger than yourself that they require no effort or attention from you at all. The Earth does not need your help turning. The Sun does not need reminding to hold its planets close. The galaxy will keep its slow, patient orbit, whether or not you are awake to think about it. So let the picture pull back one final time, the way it pulled back in an old spacecraft's last glance toward home. From the pale dot of the Earth hanging in its sunbeam, from the Sun, one ordinary star among billions, warming 8 known planets and a great deal of scattered rock and ice besides, from the slow turning arm of the galaxy that holds it. All of that immensity narrows now, gently, back down to something much smaller and much closer, a bed, a blanket, the particular weight and warmth of your own body settling into stillness, a breath moving in and easing back out, the room around you quiet and dim, the vast turning universe going on exactly as it always has, needing nothing further from you tonight. You have traveled a long way tonight without moving an inch, out past familiar planets and stranger, colder worlds, out toward comets and belts of ancient rubble, out to the edge of where our star's influence finally gives way to the dark between the stars, and now, slowly, gently, you have come all the way back, here, to this room, to this bed, to this breath. The solar system will keep turning through the night, exactly as it has for 4.5 billion years, patient and unhurried, asking nothing of you but rest. And there is more time yet to come than has already passed, more waiting quietly ahead than lies behind us, though the changes to come will unfold so slowly that no single lifetime, no 100 lifetimes, could ever notice them arriving. 5 billion years from now, give or take, the sun will begin to change in earnest, having spent the whole of its long middle age quietly fusing hydrogen into helium at its core, patient and steady, the way it has been fusing it every second since long before the Earth existed at all. When that hydrogen finally runs low, the sun will begin to swell, slowly at first and then more dramatically, cooling as it grows, turning a deeper shade of orange and then red, expanding outward until it becomes what astronomers call a red giant, a star so much larger than the one we know that it may reach out as far as the orbit of the Earth itself, or perhaps just short of it, the calculations still gentle with uncertainty on that particular point. Mercury and Venus will very likely be swallowed entirely. The Earth's fate is less certain, poised right at the edge of survival, though even if it is not consumed outright, it will be scorched beyond any recognition, its oceans boiled away long before that, its surface left as bare and lifeless as the moon's. This is not a frightening thought so much as a distant one, the kind of fact that is true in the way that winter is true in the middle of summer, real and coming, but so far off that it asks nothing of you tonight. Long before any of that arrives, the sun will simply keep doing what it has always done, rising and warming and setting, indifferent to the unimaginable stretch of time still folded up ahead of it. And after the swelling, after the red giant phase runs its course, the sun will shed its outer layers gently into space, breathing out great translucent shells of gas that will drift outward and catch the light, forming for a time one of those soft glowing rings that we now see around other, older stars through telescopes and call planetary nebulae, though they have little to do with planets at all, only an old and lovely name given before anyone understood what they truly were. What remains at the center, after all that gas has drifted away, will be a small, dense ember of a star called a white dwarf, about the size of the Earth but almost unimaginably heavier, cooling slowly across the following trillions of years, glowing fainter and fainter, a small, quiet coal at the center of what used to be a solar system, still holding whatever planets remain in their orbits, still faithfully keeping its old, patient habit of gravity, even after it has stopped producing any real light. All of this lies so far in the future that it might as well belong to a different universe entirely, and perhaps that is the most useful way to hold it, not as a worry, but as a kind of far horizon, a reminder of just how much time surrounds this one ordinary night. You exist in an almost unfathomably brief sliver of that immense stretch, a flicker so small it barely registers against the age of the star above you. And yet here you are, noticing it, wondering about it, letting your mind drift out toward red giants and white dwarfs and slow galactic turning before drifting back again, which is itself a small, remarkable thing, a universe old enough to make stars and planets and oceans having also become, in you, old enough to lie quietly in the dark and think about itself. None of that needs to be carried any further than this thought, though. The sun outside your window, wherever it currently sits below the horizon, is still young as stars go, still warm, still steady, still exactly where it has always been in relation to you, close enough to rise again in a handful of hours and find you rested. Nothing in this vast unfolding requires your attention any longer tonight. The turning has been arranged for far longer than anyone has been awake to watch it, and it will go on arranging itself, star by star, orbit by orbit, breath by breath, while you finally let go. Rest well.